So let us start with the initial condition for our oscillating harmonic oscillator. I mean, in quantum mechanics, it's not so obvious that even a thing called harmonic oscillator will show any oscillatory movement. I mean, we remember, for example, that the populations in closed system, populations of eigenstate, do not change. So if the state of my harmonic oscillator, one of the eigenstates is populated and only that is populated, we will not see any dynamics in an oscillator, especially not oscillatory dynamics. Okay, so what's our task now? Our task is to represent our sort of future solution of the dynamic problem. So my, let's say, vector, state vector, in terms of the coefficients of, and in terms of the eigenstate. So let's say here are some coefficients of the expansion. They might be time dependent, and here are the eigenstates of the oscillator. So I will have to find this I would have to find out how this evolves in time. So we will be looking for time evolution. But the question is, how does this stuff look like at t equals 0? And well, I can specify it in an arbitrary way, but my prescription or my question was, how can I express in this way the case when I just shift the initial Gaussian or the ground state Gaussian distribution somewhere else? So how can I basically shift this by some q0? And now this the fact that I draw it up here is only to demonstrate that with that shift I'm shifting also the energy. I mean, the energy of that system obviously is given by the potential energy. So at this point here I will assume I have zero kinetic energy and just shifted potential energy, which means, at least in the representation by q, that I would go from q to simply different position. But I want to change everything into a problem of first how to find the initial coefficients and how to solve their dynamics. So I will assume that my initial wave function, this assumption is actually reasonable. I'm now trying to formulate all the problem quantum mechanically. So this is my initial wave function, that it will be obtained from the ground state wave function or ground state, ground eigenstate, by means of certain operator. And this operator I will call a shift operator. So this is a shift operator. Well, and the whole discussion that I will be doing here will be about how one actually gets to this to an expression that would give me this this shift operator, and that expression, if possible, should be actually in terms of matrix elements in these states. I don't want to work in this representation as yet. I want to work in this representation, so I need the operator that makes this shift to be expressed in terms of its matrix elements in this state. All right, so well, we would have to go back to this representation, or start with this representation, because that's where we know how to shift the wave function. All right, so we will say something like this. So we have the psi 0q. That's this. Well, this is the psi 0q, and this is psi g, ground state, and ground state shifted. I hope that this is clear, that this is a definition. By psi 0q I mean this shifted wave function. How does it look like? So this is a representation of my initial wave function in the q representation. Now I can insert, we didn't discuss that, in much detail, but I can insert here the unities to represent this whole thing in terms of, I mean, including the shift operator to represent that in the coordinate representation. So let me put it this way. This is the expression we want to express explicitly in the coordinate representation. For that, I have to insert here and here the unity in terms of sum over all coordinate eigenstates. This is a continuous, this is something like sum over n, the unity, but now I'm expressing it in terms of these states here. So what I'm getting is a double integral. So there's the q dash and the q2 dashes that I have to introduce, and now I have, let's use different colors, q, that's this q, now q dash, that's the unity, now d q0, and here I introduce the other unity, the q2 dashes and q2 dashes, and here I have the psi g. Now this can be written, because here what I have here is, that's usually a Kronecker delta function if I have let's say discrete n and m, and in the continuous case this corresponds to the to a real delta function. So I'm getting rid of one of the integrals. So the result of this is one integral, let's say, over d q 2 dashes, and here is q d q0 q2 dashes psi g. So this represents an action, and again, because I can get rid of this, I mean this whole thing from here to here, that's unity. I have introduced that. I can in principle go back to this expression here, and I know how that looks like. I mean, this is a representation of this action in terms of q. I mean, I have shown here how one explicitly writes out the action of this operator in case we know how it looks like in space, but unfortunately we don't know that, and we don't even need it, because we can concentrate directly on this. This is a representation of this whole thing in terms of q, and we know, or well, we don't know, we will be able to find out how this might look like. For that, I will, let's say, because this doesn't go anywhere, I will follow a little bit different path where I will motivate how one could get to the representation of this in the first place. So what about a similar case which we would not be easily able to express in terms of an integral, and that's the case of the impulse operator. So what happens, maybe let's give it some new title. Or momentum operator. I'm using impulse and momentum as equivalent words because I'm used to both terms. Maybe this is some influence of Czech, or I don't know. So the action of an operator P, the impulse or momentum operator on psi, that is also, if I want to express it in the Q representation, coordinate representation, so this would lead to the same problem as I have here. I could write it out this way, but I'm unable to formulate, to write this element here nicely using the Q representation. But I know how the action of psi looks like. So it looks as minus I, and then derivative of the psi g q, derivative of the wave function in that representation, coordinate representation. So maybe this thing also will help me here. You know, I have here something that should be properly expressed by an integral, but in fact it's expressed by a derivative. This should not be such a surprise, because this shows that this is a non-local operation in space, and derivative is actually also a non-local operation in space, although infinitesimally non-local. Alright, so what can I do? I can be looking for an operator. What about just looking for this operator D in this Q representation directly, this same way? So I have this. Maybe I'll find something of this sort if I don't go through representing everything like this, but just represent the whole thing. And there is really a way. So how does the shift operator actually look like? Shift operator. Okay, so formally it's this. It's dq0 psi g q, and in fact it's just this. It's taking the g and shifting it. That's what we said several times. But I can express this in terms of some derivatives, as here. In fact, I can express this using Taylor series. Taylor series, which will give me the following. It's the sum over n from 0 to infinity, and there is 1 over n factorial q0 to the nth power, and then derivative of the q to the nth power, so nth derivative, and that acting on psi q. So this is a Taylor series, Taylor expansion of this function around around the value of q, and I'm expanding it by this little parameter q0. Because this can formally run to the infinity, I can say that this is exact. There is no approximation in this. Now my question is, what is this sum here? I think it should remind you something. It should remind you the definition of e to the power of a, because that is sum over n, 1 over n factorial, and then there is a to the nth power here. So what I am empowering here is this q0, and multiplied by the derivative in space. Now, because I'm shifting by minus, I should also add a minus here. So, well, let's say minus q to the nth power. Alright, so that tells me that I can now write this thing as an exponential exponent of q0 and the derivative of q acting on psi q, and this gives me a great opportunity to introduce quantum mechanical operators back into the play, because I know it hasn't been written here in this video yet, because I know that p, the quantum mechanical operator, is minus I derivative in space, which means that the derivative in space, which I need to put in here, is equal to IP, if I'm not completely mistaken. So if one multiplies this now by minus I get here minus and second minus, so it's P. Alright, and that tells me that this is equal to exponential of I q0 p operator acting on psi g q. Okay, and that's basically what I wanted, because now I see by comparison with this here that the d iq0 operator can be defined as an exponential of the iq0b operator. Good, that's perfect, because such an expression, the expression that I have here, is valid in any representation. I have written it in terms of an operator, and now I can express it in any representation I want. And our next step in the next video will be representing this operator in terms of those eigenstates of the harmonic oscillator. So we will go towards a suitable representation, and suitable means suitable for numerical calculations, suitable for our demonstration videos where we want to using octave just some matrices. We don't want to do, well, exponentials we will have to do, but we certainly don't want to do derivatives. We can do everything in terms of matrix representations of these operators.